Well, hi, everybody. Welcome back to my abstract algebra lecture series. If you're watching this video, it means you probably already saw my earlier video that was just about the basic definitions and examples of groups. And I want to pick up now with where I kind of left off in that last video. In that last video, just to remind you real briefly, we wrote down the four main axioms of a group. So when you're verifying that something is a group, technically, it has to have closure, associativity under the operation, an identity element, and every element has to have an inverse. Those are the four main axioms that are required of a group. And we wrote down a list of quite a number of examples of groups. For example, the integers, rational numbers, real numbers, or complex numbers under addition. If we throw away 0, which is what the star denotes, then we can make multiplicative groups under multiplication out of the rationals, the reals, or the complex numbers. We can also work with matrices under addition. And again, if we throw away the matrices that are not multiplicatively invertible, it will leave us with a group called the general linear group, GLN of C, under multiplication. We can also do addition mod n. And again, if we throw away those numbers that don't have multiplicative inverses in mod n, we're left with the unitary group under multiplication in mod n. So notice that example 2 is really based on example 1, where we throw away certain elements under multiplication. Same strategy is applied to number 4 with respect to number 3. And with number 6 with respect to number 5. And a couple of additional groups that we talked about in the last video that are really important and really useful to know about. The quaternion group, Q8. That's the one with the I, J, and K. The symmetric group, which is all of the permutations of an n-element set under composition. And finally, the dihedral groups. These are the rotations and reflections of a regular n-gon. Again, under composition of those elements. So these are some good examples, basic examples of groups that we want to be familiar with. In the current video, however, I'm going to point out that there's a lot more groups that we haven't even scratched the surface of yet. And in fact, there's a whole program, a whole series of approaches to making new groups that we still haven't seen out of the old groups that we already have. This is kind of a neat idea. So I've titled this video, New Groups from Old. Before I get into that, there is one little piece of loose end, I guess you could say. It's a loose end from the previous video that I wanted to address before. We're going to need it in this video. So I thought I'd start off with just a little, I'll just call this a fact. And the fact is just simply that when we talk about inverses, every element in a group has to have an inverse under the operation. The fact is that that inverse is unique. Okay, so let me just say each element of a group G has a unique inverse. Has to be unique. There can only be one, in other words. And so I'm actually going to take a moment and provide a proof of this fact. You maybe have seen this kind of argument done before. For example, this same thing is true with matrices under multiplication. If a matrix has an inverse, that inverse will always be unique. So let's actually prove that here. And of course, the way we prove uniqueness is we suppose that there are two of them. Suppose that we have an element, I'll call it A in my group G, has two inverses. Let's call them D1 and D2. This, of course, just means, if I want to write out what that means, that just means that A star D1 is equal to the identity, which is the same as D1 star A. I'm just reminding you, this is the definition of an inverse according to the basic properties of a group here. And we also know that A star D2 is also equal to the identity element. So we have these two sets of equations, and it is really just a quick little one-line proof. And what we're going to do, of course, to prove uniqueness, guys, and you've seen this, I'm pretty sure you've seen this kind of reasoning before, we're going to just prove that D1 is equal to D2. In fact, if you'd like, feel free to pause the video and see if you can fill in the missing steps. This is just a one-line proof. It's not too difficult, but if you've seen this before and think you have an idea, feel free to pause the video and give it a try. But I'm going to go ahead now and show you how to finish this. Essentially, it's just a simple little trick. What we do is we start by just multiplying by E. So we take D1 and we multiply it by E, which is like multiplying by 1, right? It's a safe thing to do. And then we take the E and we rewrite it as something else. I'm going to rewrite it as A times D2. Like that. And I can see I didn't give myself enough room. I lied. I said this was, well, yes, it will be a one-liner if I just keep going over here to the far side. I'm going to use the associative property to reorganize the parentheses here. Okay, so I can put the parentheses around the D1 and the A, but of course D1 star A is just E again. So we get E star with D2, but E star D2 is just D2. So there you go. With a little fudging, I managed to make that into a one-line proof. Okay, so every element in a group has to have an inverse, and that inverse has to be unique. Okay, and so we actually have a notation, which is that the unique inverse of my element A is written, well, in multiplicative notation anyway, we would write it as A to the -1 power. Be a little bit careful. This does not mean 1 over A. And of course, the group could be with a different kind of operation, such as addition. Under addition, it's not very normal to use these kinds of negative exponents when you're talking about the inverses under addition. You usually put a minus sign, right? The inverse of 3 is -3. It's not 3 to the -1, right? So this is really being written in a multiplicative format, as if the operation was multiplication, but we need to be sort of flexible with our interpretation of this. And remember that there are groups for which the operation is not going to be multiplicative, and it doesn't make so much sense to use negative exponents as if we're going to be forming reciprocals or something. So want to be a little bit careful about that. Okay, I would like to, having got that behind us, feel free to pause if you need to catch your breath and think about what we've put up here. It's just, you're going to see me using this inverse notation today. I wanted to come back to the main topic, though, of this video, which is new groups from old. And I'm going to give you sort of 2 ways of creating new groups from old. Okay. So new groups from old, I guess I'll start here. The first one is with something called direct products. And this one does not take a huge amount of explanation. It's a pretty simple thing to do. What we're going to do is start with 2 groups. So given the groups, let's say G1 and G2. Okay. We form a new group, which is G1 cross G2. So this is a direct product of the groups G1 and G2. And this is the set of just simply pairs of elements, little g1, little g2, where little g1 belongs in the first group and little g2 belongs in the second group. Okay, That's how it basically works. And of course, if we wanted to take an element and then multiply it with another element, so let's say we take G1, G2, and we want to multiply it with, I don't know, X1, X2, thing like that. Of course, the way we're going to do that is we're just going to work within each slot and calculate the result within each slot. So G1 star X1, that's happening in the group G1. And the little G2 star with the little X2, that's happening in the group G2. And so this is a formula for how to multiply the elements. So just be a little careful, like this first star is like within the first group, this second star is within the second group, and I'm now defining yet another multiplication, another star that deals with the entire ordered pairs. But you can verify that as long as G1 and G2 are groups and have closure, associativity, identity elements, and inverses, then so will this, okay? And this is a larger group. I will just note that the size, this is no surprise. If you want to know how many ordered pairs could you make like this, well, the answer is that you would multiply the size of G1 with the size of G2. Okay, so we can build interesting groups of whatever size we want, right? So let's just think of an example. Let's construct a non-abelian group of size 80, just to play around with some of the examples that we did on the previous video. Well, 80 is, not any particular special number, but I know that I can obtain it by multiplying numbers together. For example, feel free to stop the video, by the way, if you want to think about it first. But 80 is just 10 times 8. So couldn't we just take a group of size 10 and multiply it by a group of size 8? That'll give us a group of size 80. So just as an example, maybe for the solution here, there's lots of right answers here, but we could take, C10, that's a group of size 10, and cross it with a group of size 8. And if I want my overall group to be non-abelian, then I want to make sure that at least one of the two groups that I'm crossing together is already non-abelian. So a non-abelian group of size 8 brings us back to some of our early examples of groups. There's many choices here, or at least a couple choices. Q8 would be one example, but you also, if you prefer, you could have crossed Z10 with D4. Remember the dihedral group on the square? There'd be 8 rotations and reflections of a square. So these are just a couple of examples. Maybe you could think of some other things that we could do. But this is at least a start, a couple of non-abelian groups of size 80. Okay, so we can form direct products of groups and build larger groups out of that. That is one natural construction that we can do. Feel free to stop if you have any moment to ponder on that. I am going to erase this and give you a second strategy for creating new groups out of old groups. And that strategy is to actually go the opposite direction and form something that is smaller than the original group. Namely, the second approach here is something called subgroups. We're going to talk for a few minutes about subgroups. So let me start you off with just the definition of a subgroup. So by definition, what is a subgroup? Well, you have to have a group G to begin with. So let G be a group. Notice I'm suppressing the operation at this point. I'm not continuing to write down the star all the time. I'm just going to call G a group. There is obviously going to be an operation in the background there. And I'm going to take a subset. I'm going to call it H, which is a subset of G. Okay, it's just a subset. So this is the notation. Let's be careful. This is a subset notation. Okay, so it's just inside of G. If H forms a group, if this H happens to form a group in its own right, and I'm just going to emphasize that when it does that, when it forms a group in its own right, it has to be using the same operation as G. That's actually kind of important. So for example, some people might look at Cn and kind of think of it as a subset of C. Right, so Zn, remember those were those congruence classes from 0 up to n-1. And of course, those integers are part of the larger set of all of the integers. But the operation in Zn is mod n arithmetic, right? You're doing addition in mod n. But got to be careful because in the integers, you're not doing mod anything. It's a different operation. And so I would not call Cn a group in its own right with the same operation as the big group G. In this case, that wouldn't be true. So it has to be using the same operation as G. Then, as long as that's the case, H is what is called a subgroup of G. And this is often written with a less than or equal to symbol as opposed to just a subset symbol. In my experience with teaching this class, I find that sometimes people are a little sloppy between subsets and subgroups, right? And of course, the symbol is very similar, but we need to be very clear about the difference. A subset isn't really much of anything from an algebraic point of view. We don't care that much about it. The question is, does it form a group in its own right with the same operation as G? Then if it does, now we have an algebraic interest in it. It's actually a subgroup in that case. Okay. Let me write down a couple of examples. The first example is that for any group G, we always have two subgroups of G that are kind of automatic. They're very trivial in nature. So we have, in fact, they are called that. They are called that. We have the trivial subgroups. Well, specifically the trivial subgroup that I want to emphasize here is just E by itself. Okay, if you're ever looking for an example of a very boring group, this would do it. It's just 0 or 1 or depending on the operation. It's a single element. Obviously, E star E is just E. It is the identity element and is the only element in this subgroup. So this would be my H right here, would just be this singleton identity element, just like that. So that is the trivial subgroup. E and the whole group itself. That's also a very boring subgroup. You can actually say that, so what we're saying here is we're saying that the identity by itself is a subgroup of G, and G itself is a subgroup of itself. Okay, so not terribly interesting, either one of those examples. Okay, but it's still good to think about those things. Let's do a slightly more interesting example. Let's take G to be Dn. Remember, this is the dihedral group on a regular n-gon. And let's let H be the set of rotations only. Rotations of a regular n-gon. The set of rotations of a regular n-gon. Again, with the same composition of operations that Dn is a group with. So remember, Dn is all rotations and reflections. It has a size of 2n. Okay. But here we're talking about rotations only of a regular n-gon. This is what we're looking at right now. Well, if you compose two rotations together, closure, right? If you take a rotation and then you follow it with another rotation, haven't you just created one big large rotation? Right? Absolutely, it's closed. It's definitely a closed set. It's still associative because after all, you're just composing rotations together. Doesn't matter, how you parenthesize that set of rotations. The identity element, that's just like doing nothing. It's like rotating it 0 degrees. You're not even actually doing anything, but it's still considered a rotation of 0 degrees. And of course, the inverse of a rotation is to just backwards rotate by the same amount, which technically is still a rotation, just in the opposite direction. It's still going to be in this set of rotations. So H has inverses, it has closure, it's associative, there's an identity element. And so in fact, this is a good example of a subgroup. It is in fact a subgroup. Okay. Now, if I just took only the reflections, so maybe I'll leave this for you guys to think about as an exercise. The set of reflections of a regular n-gon, that set is not, and I like to use just a slash, this is a good notation to practice, put a slash through your less than symbol, that it is not a subgroup of Dn. Well, it doesn't have an identity element, right? The identity element was that rotation through 0 degrees. So the identity element is not a reflection. It's not part of this set H right here. And so we don't have a subgroup. It didn't form a group in its own right. Okay, great. Let's do one more example of subgroups. Do another example here. So this will be number 3. Let's just let G be, let's use that general linear group just to practice that a little bit. So remember that this is in this case, 2 by 2, so GL2, 2 by 2 invertible matrices. Okay, and I'll allow the complex numbers as entries of those matrices. Really, that isn't quite so important. So that's my group, and I'm going to make a subgroup. It's going to be the set of all matrices that look like the following: 1A, 0, 1, such that A is a complex number. Okay. So it's matrices like this. Now notice that these matrices are invertible. If you check the determinant of this little 2 by 2 matrix, it's not 0, right? The determinant is 1 times 1 minus 0 is just 1. It's not 0. So the determinant is not 0. So these are all invertible. So it really is legitimate to call it a subset at least. It has to start, the first thing is it has to be a subset of G that has to actually consist of invertible 2 by 2 matrices, which it does. The determinant verifies that for us. But then we have to ask ourselves, okay, what about these axioms, the rest of these axioms here? So we can check the axioms of a group. Because H, if it's a subgroup, it has to be a group in its own right. So it has to have closure, associativity, and so on. So the first one, of course, closure. Well, I take 2 elements out of H. So let's do that. Let's take 1A, 1 and 1B, 1. These are elements of H. So we start with 2 elements of H. And what I need to do is multiply them together. Now, this group is a group under regular matrix multiplication. So I'm just going to do the verification here. I don't have to show a lot of work. I just have to sort of calculate this thing out. Looks like I'm going to get an A plus B in the upper right corner. That's going to be the key thing. This is the result of doing that matrix multiplication. So I have to stare at that element now and ask myself, is it still in H? In other words, is H closed? Well, let's see. Does it look like, here's H right here. Does this element look like it lives there? It sure does, right? A plus B is, of course, just playing the role of little a right here. It's a complex number. It sure is. This is an element of H. Absolutely. Okay, great. And secondly, then, we have to check the associative property. Now, here's the thing, guys, with the associative property. You know, we're just verifying, aren't we, that matrix multiplication in this specific subset H is associative? But we already knew that the whole big group of all invertible matrices was a group. It was already associative under multiplication in the big universe G. So what I'm going to claim here, guys, is that associativity is inherited by H from G. It's actually inherited. It gets inherited by H from G. You don't have to stop and actually check that again. The closure is important. That's not so obvious just from the outset. But associativity, we don't have to stop and check it because G is already associative and all we're doing is working inside of G. So of course, everything inside of G, even if it's inside of H too, is associative. But we get away without having to do that. My identity element, that's the third axiom. If I just take a look at that element, it sure does look like it has the right form of anything that's living in H. So this is certainly inside of H, and I can just check that off immediately. And then finally, I have to think about inverses. I have to think about the inverse of an element. So let's take just the first element from H that we had up here before. So 1A, 0, and 1, that's an element out of H. And let's think about its inverse. We know it has an inverse because this matrix is invertible. The question is, what is the inverse of that? Well, if you take a linear algebra course, they're going to teach you the formula for the inverse of a 2x2 matrix. And it turns out that in this case, the answer is 1, negative A, 0, and 1. Now, if you didn't believe me, of course, you could take that proposed inverse and multiply it by the original element, just do matrix multiplication, and verify that you actually get the identity element E again. But that's a pretty simple calculation. Just take these two things that I've circled, multiply them together. I'll let you do it. You will get E, right? And this inverse is in the right form to belong into H again. So this is still in H. So you have now verified these axioms. It's quite nice. We've been able to verify the axioms of a group for H. And so the conclusion is, thus, H is a subgroup of G. It's a nice example. It's a nice example of a subgroup. Okay. Now, I actually want to take a moment and notice something about this verification that we did here. It actually can be kind of generalized into a theorem. And in the textbook by Hungerford, this is theorem 7.10 on verifying subgroups. Theorem 7.10. So here is what this theorem says, and then we'll look at it in the context of the example that we just finished. So I'm going to start off by letting G be a group. And H is a subset of G. Okay. So G is a group, H is a subset of G. Then here is what we can do, guys. I want to have a theorem that tells me when H is a subgroup. Then H is a subgroup of G if and only if, and I'm going to put the condition over here on the right side. What I'm actually going to do, guys, is give us a cheaper way of checking that H is a subgroup without having to check all of these axioms. It turns out that we can do that. Namely, there's just two things we need to do. H is closed under star. So that's actually the first axiom of a group, closure. So we still check closure. But notice that we didn't need to check associativity. It was inherited by H. Well, that's always going to be possible to say because H is always sitting inside of this big universe of G. So we're going to skip the associativity check all the time. Okay. And in fact, we can skip all the way down to the last condition, which is that H is closed under inverses. Okay. Actually, if H is closed under multiplication and it's also closed under inverses, then it's actually got to have an identity element in it. It's going to have an identity element in it as well. And so that's it. That's all you have to verify. So in other words, the first and fourth part of what I checked here, the first and fourth axiom of a group is really the key. And so that's the main point that this theorem is trying to help us with. It's giving us a nice shortcut, sort of acknowledging that associativity doesn't need to be checked. And really, we don't even need to check the identity element. Okay, so let me take a moment and do the quick proof of this. It's kind of a theoretical class, so we have to do some proofs once in a while. So let's try to prove this. This is an if and only if. I'm going to prove it in both directions. Okay, of course, the forward direction is actually easy because if we assume that H is a subgroup of G, well, then it has to have these axioms, right? It has to be already closed and already have inverses, right? So then little a and little b hold for H by the definition of a group. Remember, if H is a subgroup of G, it means it is a group in its own right? We're assuming that H is a group. It's a subgroup, so it's a group. So it already has these axioms. Specifically, it has closure and inverses being preserved. So nothing else we have to say about that part of the proof. That becomes an automatic conclusion. Okay. But now let's go in reverse. Let's assume A and B, which really means that we're assuming 1 and 4 in my list of axioms of a group. Let's suppose that H is closed under the operation and that it is closed under inverses. I'm just going to note that H inherits, so this actually now makes it into the general proof, it inherits associativity from G. Right? G is already a group, so G is already associative, and H is inside of that. So H is already associative just because it inherits it from the big universe of G. So we assumed closure and inverses. We've now inherited associativity. What about the identity element? Well, that's going to be pretty easy as well. What we can do for this part, I'll just take an element out of H, call it A. And then from the condition B, which we are assuming, H is closed under inverses, so the inverse of A has to also be an element of H. And then from condition A, we also know that H is closed under the operation. And so A star A inverse has to be an H, but A star A inverse is just E. So H has an identity element as well. And so we've now verified that H is a group. H is a group, and it's inside of G. So it's actually therefore a subgroup. Remember, a subgroup is just a group that's inside of a bigger group. So H is now a subgroup of G. Okay, so we really, anytime we're trying to verify a subgroup, that's all we have to do. We just have to check that H is closed under the operation and that it's closed under inverses. Feel free to pause the video if you need to. I'm just going to erase the proof now for a moment. But it is always findable again on this video if you just back up. We can actually improve this theorem even a little bit more. I just want to mention this as well. I may not go into the details of this. An even better improvement of theorem 7.10, we can actually get it down to just one condition. Namely, that H is a subgroup of G if and only if, okay, for all A and B in H, we have, so see what you can do is you can combine the closure under the operation and closure under inverses into a single condition, which is A times B star. B inverse, I'm sorry, A times B inverse is still inside of H. So, again, if you know little a and little b, then you would need to prove this, right? But again, it's very easy because you're just combining. So if you just start with A and B here, right, that are in H, then because of closure under inverses, B inverse is in H. And then because of closure under star, A times B inverse is in H. So you get this conclusion once you already know that you have the closure under the operation and under inverses. And conversely, well, if you know this condition right here, then you can very quickly verify, for example, you could just take, if you just took A to be the identity element, if it's just the identity element, then what you're saying is that if B is in H, then B inverse is in H. That sounds like closure under inverses, right? And closure under the operation, this is the operation A star. I mean, you could replace the B inverse with B, and then you've got A times B is in H. So it's pretty trivial. I'm not going to write it down at the moment. If you feel that it would help you to sort of really try to write that all out, I encourage you to do that. But for the time being, I'm just going to call that good and just let that go. Okay, great. Well, this is a quick introduction to forming subgroups. There is a lot more to say about subgroups, actually. I'm going to save that for another time. We can actually create subgroups simply by taking elements and taking powers of, just take a single element out of G and just start raising it to powers until you get something that's a closed structure under the multiplication. This is called a cyclic subgroup. And it's just a natural construction. It's a very easy thing to do. But I'm going to wait and save that for another video. This is just a little teaser to get you thinking about that a bit. But hopefully the concept of a subgroup is resonating a little bit here? The idea is that as long as we have a subset of something that's already a group, we already have a big group, a big universe in place, then inside of that group, we can construct subgroups as long as they are closed under the operation and under inverses. That's all we have to worry about. The associativity is in the background. The identity element will take care of itself. It's really just the closure that we have to verify under the operation and under inverses. It's kind of like with a subspace of a vector space. For those of you who've seen a little bit of linear algebra, if I want to verify that something is a subspace, I don't have to check the whole big long list of vector space axioms. All I have to check is that I have something that's closed under addition and closed under scalar multiplication, which are the operations in a vector space. Well, we're doing the same thing here, except it's not addition and scalar multiplication. It's whatever the operation is and whatever inverses look like. And we have to check the closure under those two things. But it's a very, very similar, should be almost reminding you of doing that subspace verification in a linear algebra class. I hope that this has been helpful. I hope that you've been taking good notes. If you have any questions about what I've been talking about here, I hope that you will get in touch with me. I'll be happy to answer those questions as best I can. But hopefully it makes some good sense, and we'll keep practicing this and getting better at it. I look forward to seeing you guys again next time. Thanks so much for your time. Bye for now.